Hello, welcome back to a new video. We were discussing continuity, section 1.5 of chapter Limits and Continuity from the textbook Calculus and Analytic Geometry 9th edition by G.B. Thomas and R.L. Finney. Today we can see continuity on intervals. There we can see intermediate value property and also intermediate value theorem. Okay, we can go to the video. When a function is said to be continuous, we have seen continuity at a point, at interior point, at left hand point and at a right hand point. If a function is continuous everywhere in its domain, it is called a continuous function. A function that is not continuous throughout the entire domain may still be continuous when restricted to particular intervals within the domain. For example, we can say the function 1 by x. Here this function is not continuous in the domain minus infinity to infinity. Here it is discontinuous at a 0. But this portion is continuous and also this portion is continuous. Or we can say in the interval minus infinity to 0, this function is continuous. And also in the interval 0 to infinity, this function is continuous. It is discontinuous only at a 0. So if we are considering the entire domain, this function is discontinuous. But when we restrict it to the intervals, this function is continuous. So here we see the importance of discussing continuity on intervals. We know continuity on an interior point. A function is said to be continuous at an interior point x is equal to c if limit extending to c f of x is equal to f of c. And also we have seen the continuity at the end points. Now a function is continuous on an interval I in its domain if limit extending to c f of x is equal to f of c at every interior point c. And if the appropriate one-sided limits equals the function value at any end points I may contain. And at the end points of I, at the left hand point and at the right hand point, the appropriate limit equals the function value. That is, at the left hand point, if the interval is say AB, at the left hand point A, left limit is equal to the function value. That is, limit extending to a plus f of x is equal to f of a, and at the right hand point b, limit extending to b minus f of x is equal to f of b. So a function is continuous on an interval I in its domain if it is continuous at every interior point and it is continuous at any endpoints I contain. We know polynomial functions are continuous everywhere in the real line. So polynomial functions are continuous on every interval. And rational functions are quotient of polynomial function. So rational functions are continuous on every interval on which they are defined. We can see more example. We have discussed the graph of semicircle, a root of 4 minus x square. We have already seen this graph. 2 minus 2, 2, 0. Y equal to root of 4 minus x square. This function is continuous on the interval closed interval minus 2, 2. Here continuous at both the endpoints also, so closed interval minus 2, 2. Here in the open interval we need not to check the continuity at the endpoints. Here a and b are not included in this interval. But if it is closed interval, we have to check the left hand point and the right hand point. If interval contains the end point, we have to check the continuity at the end points. Otherwise, all interior points enough. Next example, we can say we see the graph of unit step function. Here open at a 0 open and 1 to infinity. See, this function is discontinuous. if we consider the whole domain, that is minus infinity to infinity. But we can say it is continuous from minus infinity to 0. 0 not included. At 0 it is not continuous. Here the function value is 1. Here limit is 0. So we can say this function is continuous in minus infinity to 0. This portion is continuous, and also 0 to infinity including 0. It is continuous from 0 to infinity. Also the functions sin x and cos x. We can say y equal to cos x. Cos x is continuous on minus infinity to infinity. A function f is said to be continuous on an interval I in its domain if limit extending to c f of x is equal to f of c at every interior point c, and if the appropriate one-sided limit equals the function value at any endpoints I may contain. That is, a function is continuous on an interval I in its domain if it is continuous at every interior pointer c, and also if it has any end pointer, then it should be continuous at that end point also. If it is closed interval AB, then it should be continuous at the both end points. If it is open interval A, closed interval B, then it should be continuous at the right end point. Okay. If it is open interval AB, we have to check the continuity at the interior point only. Okay. Functions that are continuous on intervals have some properties. One of this is intermediate value property. A function is said to have intermediate value property if it never takes two values without taking on all the values in between. That is, we can say, if this is a function, if this is the point P1 and P2, then this is f of P1 and this is f of P2. Intermediate value property is if a function takes the values f of P1 and f of P2, then it takes all the values in between f of P1 and f of P2. See, it takes all the values in between f of P1 and f of P2. We can write a function is said to have the intermediate value property if it never takes two values without taking on all the values in between. Intermediate value theorem says that a function that is continuous on an interval I has the intermediate value property. Or we can say, suppose f of x is continuous on an interval I and a and b are any two endpoints of AB. So that is I closed interval AB. Then if y0 is a number between f of A and f of B, there exists a number c between A and B such that f of c is equal to y0. That is, if f of x is continuous on any interval AB, and if y0 is a point in between f of A and f of B, there exists a c between A and B such that f of c is equal to y0. We can see a function like this. Here f of A is this one, f of A, and f of B is f of B. Okay. If we take any arbitrary pointer y0 in between f of A and f of B, there exists a c between A and B such that f of c is equal to y0. This is the intermediate value theorem. We can write the theorem as, suppose f of x is continuous on an interval I and A and B are any two points of I. I is any interval and A and B are any two points of I, that is AB is contained in I. f is continuous on all I. Then if y0 is a number between f of a and f of b, there exists a number c between a and b such that f of c is equal to y0. If f is continuous on the interval I, then a closed interval ab is contained in I. Then f should be continuous on the closed interval ab. So it takes all the values in between f of a and f of b. The continuity of f on I is essential to this theorem. If f is discontinuous at even one point, the theorem conclusion may fail. We can see the example of step function. Here it is discontinuous only at 0. It does not take the values in between 0 and 1. See. Or we can say the greatest integer function between the interval 0 and 1. What is this function? 0, 1. Here 0. At 1 it is 1. All other values it is 0. Up to here this value is 0. This does not take any value in between 0 and 1. Here is f of 0 and f of 1 is equal to 0 and 1. But it does not take any value between f of 0 and 1. Okay. Now we can see two important consequences of intermediate value theorem. We know that graph of continuous functions are connected. It cannot have any breaks. We can see the graph of semicircle. It is connected, no breaks. Or we can say the graph of continuous functions will be connected a single unbroken curve. It cannot have any jumps or any branches. We can see the graph of a step function. It has a jump, it is discontinuous. And we see the graph of 1 by x. It has two branches, it is discontinuous. Next is a consequence for root finding. What is a root or a zero of a function f? We know that the solution of the equation f of x is equal to 0 is called a root or zero of f. By intermediate value theorem, we can say that if f is continuous, then any interval on which f changes a sign must contain a zero of the function. We can see, suppose f of x is continuous. Consider this graph and consider the interval a, b. Here f of a equal to this one and f of b equal to here. Here in this interval AB, f changes its sign. That is, f of a is negative and f of b is positive. It changes its sign. So this interval has a root of f. Here f of a is negative and f of b is positive. 0 lies in between negative numbers and positive numbers. That is, f of x is equal to 0 at some x in the interval AB. Or we can say there exists a c such that f of c is equal to 0. That is, for continuous function, any interval that changes its sign has a root of that function. We can see an example. Example, is any real number exactly 1 less than its cube? If there is any real number x that is 1 less than its cube, that is equal to x cube minus 1. This we can write x cube minus x minus 1 equal to 0. That is, it's enough to check the function f of x is equal to x cube minus x minus 1 has a root. Or we can say we have to find an interval where f changes its sign. See, what is f of 1? F of 1 equal to 1 minus 1 minus 1. That is minus 1. What is f of 2? 2 cube minus 2 minus 1. That is 8 minus 2, 6 minus 1, 5. Here in the interval 1 to it changes its sign. Minus 1 and 5. We can say by intermediate value theorem there is at least one number in between the interval 1 to where f is 0. Therefore we can say there exists a number such that it is 1 less than its cube. We can see more exercises. Exercise. First question. A continuous function y equal to f of x is known to be negative at x is equal to 0 and positive at x is equal to 1. Why does the equation f of x is equal to 0 have at least one solution between x is equal to 0 and x is equal to 1? Illustrate with a rough sketch. Simple question. Just the answer is intermediate value theorem. Here we have a function y equal to f of x. Given f of x is negative at x is equal to 0, or we can say f of 0 is negative and positive at x is equal to 1 and f of 1 is greater than 0 positive. Why does the equation f of x is equal to 0 have at least one solution between x is equal to 0 and x is equal to 1? Since the function is continuous, we know by intermediate value theorem it takes all the values in between f of 0 and f of 1. Here f of 0 is less than 0 and f of 1 is greater than 0. 0 lies in between f of 0 and f of 1. Less than 0, less than f of 1. 0 lies in between f of 0 and f of 1. Therefore, by intermediate value theorem, there exists an x between 0 and 1. That is 0 less than x less than 1 such that f of x is equal to 0. We can make a rough sketch. A negative value, say minus a, positive value, say plus b. Okay, and 0, 1. We can draw this. Okay, this is f of 0 negative and this is f of 1 positive. Okay, therefore by intermediate value theorem it takes all the values in between f of 0 and f of 1. 0 lies between f of 0 and f of 1. Simple. Next question. Explain why the equation cos x is equal to x has at least one solution. Cos x is equal to x. We can write cos x minus x is equal to 0. We know cos pi by 2 and cos minus pi by 2 are 0. See, when x is equal to pi by 2, this equation becomes cos pi by 2 minus pi by 2. Cos pi by 2 is 0, which is equal to minus pi by 2, which is less than 0. And at a minus pi by 2, this one become cos minus pi by 2 minus pi by 2, which is equal to 0 minus pi by 2, that is plus pi by 2, which is greater than 0. If we take this function as f of x, we can say f of pi by 2 is less than 0 and f of minus pi by 2 is greater than 0. That is 0 lies in between f of pi by 2 and f of minus pi by 2. Therefore, by intermediate value theorem, we can say that there exists c such that f of c is equal to 0. That is, this function has at least one solution. Next question. Show that the equation x cube minus 15x plus 1 equal to 0 has 3 solutions in the interval minus 4, 4. Closed interval minus 4, 4. Here the function is f of x is equal to x cube minus 15x plus 1. We can see the value of f in this interval. Okay. F of minus 4 will be, substitute minus 4 in this equation. We will get it as minus 3. Now f of minus 3. F of minus 3 will be 19. Now f of minus 2 equal to 23. F of minus 1 equal to 5. Here in the interval minus 4 and minus 3 there is a change of sign. So we can say there exists a root in between this interval. For minus 4 less than x less than minus 3 there exists a root. Now f of 0 equal to 1 and f of 1 equal to minus 13. Here again a change of sign. So there exists a root in between 0 and 1. F of 2 equal to minus 21 and f of 3 equal to minus 17 and f of 4 equal to 5. Again a change of sign. Therefore there exists a root in between 3 and 4. So we have got 3 roots. One in between the interval -4 and -3, another one in the interval 0 and 1, and a third one in the interval 3 and 4. Also see, this is a third degree polynomial, and a third degree polynomial can have at most 3 roots. These are the only roots of this equation. Next question, show that the function f of x is equal to x minus a the whole square into x minus b the whole square plus x takes on the value a plus b by 2 for some value of x. We have to prove that f of x is equal to a plus b by 2 for some x. F of x is x minus a square into x minus b square plus x. What is f of a? F of a equal to a minus a square into a minus b square plus a. A minus a is 0. Therefore, we get f of a equal to a. And similarly, f of b equal to b. b minus b square is 0. This term cancel, then b. Without loss of generality, we can take a less than b. If we have any two numbers, then one number is less than the other one. If a is not less than b, we can say b less than a. Okay. So without loss of generality, we can take a less than b. Where is a plus b by 2 here? A plus b by 2 is at the middle of this a and b. Or we can write a less than a plus b by 2 less than b. Here see, this function is a continuous. Just a polynomial function. And also f of a and f of b. We have a and b. Therefore, it takes all the values in between f of a and b. A plus b by 2 is lies in between a and b. It takes all the values in between a and b. That is, f of x is equal to a plus b by 2 for some x. And also we can say this x lies between a and b. There exists a x in between the inputs a and b. AB, such that f of x is equal to a plus b by 2. To understand the concept, it's enough to practice as many exercises as possible. Then only the concept will become clear to you. Okay, see you in the next video. Till then, bye-bye. If you find this video useful, please don't forget to like, share and subscribe. Thank you.